And welcome in today's Advanced and Array Signal Processing lecture. So let's start with the overview of the previous lecture. So we started this signal reconstruction subsection with slides 1 up to 15. So let's see first what we have here. 1 up to 15. So first, our data model. So here we have the same matrix of measurements x, which is equal to the multiplication of array steering matrix times the matrix of, let's say, the signal sources plus our additive white Gaussian noise matrix. And here first we estimate direction of arrivals. So we can use music algorithm, Aasp type algorithms, for example, MVDR or periodograms. Then, based on these special frequencies, we can calibrate our array. So we will have this matrix A calibrated to our special frequencies for these sources. And then main thing here, how we can estimate the signals. So estimation of matrix S. In this case, our goal is to obtain a linear estimate of this matrix S with the following values inside of vectors. So here we have the same special frequency, let's say, covariance matrix of the measurement matrix. We have the same thing, and if we assume a special case with additive white Gaussian noise, correlation matrix of the noise will be equal to the variance of the noise times identity matrix of size m, where m is the number of array elements here. And then the main idea here that we have no training sequences, and we somehow need to obtain these signals S of T sub m. In this case, we can use least-square solution, which is the simplest algorithm in this case. We need to calculate the pseudo-inverse of A. And this pseudo-inverse of A we will use as the weight vectors for our this weight matrix, double the Hermitian. So I think, let me show it here. So we write all these things like this one, and W Hermitian is the pseudo inverse of A, and in this case the estimate of our sources will be just W Hermitian times measurement matrix X. Then we have second algorithm, MVDR or BLUE, where BLUE is best linear unbiased estimate. And here we assume two cases. In first, we minimize the variance of the ith estimated signal with, let's say, subject to this zero forcing constraint. Or on our hand, we want to minimize the variance of the error for ith signal with the same constraint, so subject to this zero forcing constraint. And as the result, we have the same W here, and here. So you can see we have the same values, but of course here we add identity matrix of size D, which is the same to this. So then we use inversion lemma, and we can rewrite all these things using noise subspace, because the main idea in MVDR is to use the noise subspace instead of the signal subspace. And here, so let me show it on slides. We use ranging multipliers, and then this matrix inversion lemma, and for inverse of and as the result, we have double V equal to the inverse of the noise subspace, or let's say not the noise subspace, but the special correlation matrix or special correlation matrix of the noise times A, and all this thing is multiplied with the inverse of A Hermitian times inverse of R and N times A. And special case here, if we assume additive white Gaussian noise, our MVDR solution will be equal to the least square solution. And this solution is unbiased, because if we assume the multiplication of double Hermitian with A, it is equal to the identity matrix. And now let's continue this subsection with the last solution, which is called as Wiener solution or MMSE solution. And here we will see that this solution, in comparison with previous blue solution, will be biased. So today is lecture number 25. Lecture 25, 2022, November 29th. And here the last solution is MMSE solution. MMSE solution. Or let me check the Wiener solution. Yes. Wiener solution. So let's use 3 underlines as before for the name of solutions here. 1, 2, and 3. And let's start with slides. So we use the same minimization problem here as for MVDR, but without constraints. So you can see we use this minimum mean squared error, or we can say that we minimize the variance of the estimation. So here we have the same estimation error as before, and our goal is to find d weight vectors omega I Hermitian that minimizes the variance of the estimation error. So this thing is like goal B for MVDR, but we have no constraints here. So let's maybe, so we need to find the weight vectors that minimizes the variance of the noise of the estimation error, sorry. So here we have the same estimation error. So let's start with this thing, which is S sub I of t minus the estimate, or we can rewrite this thing as the original signal minus our weight vector for ith source and received signal x. So this is our estimation error. Estimation error, and here for this solution, let's write our goal. So for this one, with 2 underlines, our goal is to find small d where this thing is equal to the number of sources, weight vectors omega I Hermitian, I think. Let me check just for a second. Yes. And also we can add here for x, but this one for time t. Weight vector omega I Hermitian that minimize the estimation error if we use mathematical representation, it is equal to the expected value of the variance of this error, I think. Yes. So E sub I absolute value of t squared. So this is our goal. Let's put our goal into a box, and then I will add that here we do not have any constraints. So no constraints if we compare it with MVDR solution. And then we will go for this solution as before, using slides, and we will write down only the final results. So what we have for matrix W Hermitian, so for our weight vectors. So here, of course, we start with Wiener-Hopf equation, where Rx is correlation matrix of our measurement vector. Oh, yes, measurement vector. Here you can see x of t times x of t Hermitian. And for this vector p sub I, it is cross correlation between our received or measurement vector and the complex conjugate of the original signal. And here we can, for example, start with this equation, I think, that the estimate of S is equal to W Hermitian times X, where W Hermitian is equal to the correlation matrix of the signal times A Hermitian times inverse of Rx. And of course, we can find Rx using this equation and RSS using this equation where we use the pseudo inverse of A. So, matrix S we've had, so estimate of S is equal to W Hermitian times X, where W Hermitian is. So maybe I will use the signal from computer. So RSS times A Hermitian times A Hermitian times Rx inverse and times X. So this thing is W Hermitian. And then Rx is equal to the 1 over n times x times x Hermitian. So we average over the n snapshots here, and RSS is equal to the pseudo inverse of A times here we have Rx minus Rn. And of course, let me check. So this one is the estimate of Rx, and this one is the estimate of RSS. Minus relation matrix of the noise with estimate. And the last value here is the Hermitian of the pseudo inverse of A. let's go to the next slide, and then I will one more time switch to my pages here. So what we need next? So of course we can assume this special case with uncorrelated signals. In this case, RSS will be equal to the identity matrix, and for W, we will have this thing. So, and so yes, before we use the Hermitian of it, so RSS, A Hermitian, inverse of X, here we have inverse of X, A RSS. So we put identity matrix for RSS here, and we'll have only the inverse of the correlation matrix of measurement matrix times our array steering matrix. And here, yes, using these equations, we can see that it will be unbiased, this solution. So how we show this thing? Let's maybe write first the final axis, and then we will show what we have if we multiply double Hermitian with E. So switch here, final results. So we will rewrite double Hermitian here. So using MMSE solution or Wiener solution for the D weight vectors, which is collected to one matrix, we will have the following values. So multiplication of matrices RSS, Hermitian of A, and inverse of RxX. And for example, here we have no these training sequences, so how we can do all these things? So we collect our measurements into measurement matrix X. Then we find this matrix RxX, the estimation of RxX. If we look inside of this thing, I think this part we can find with signal subspace estimation and noise subspace estimation. Then, so it is, let's say, noise subspace of RxX. In this case, is equal to, not equal, approximately equal, for example, to RNN. Maybe like this one, or we can find RNN, or find RNN let's say from statistics. So we listen our channel for some time. We collect with statistics. We can approximately estimate the correlation matrix of the noise, and then at some point we will receive our signals, and based on previous statistics we find this RNN, and we can use this thing to find RSS. So we compute this one, and of course we know the A Hermitian. So that's all, and one small note for MMSE solution. Let's write down note that but I need to check, can we use covariance matrix of noise as the noise subspace of RSS? I think this have some ideas inside of this one. So what we need to note here. So first we need to assume that RSS is non-singular. Assume RSS is non-singular. In this case, we can rewrite W Hermitian as follows. So W Hermitian equal to multiplication of RSS times A Hermitian, and here instead of RSX we write down the A times RSS times A Hermitian times A Hermitian plus RNN. And then let me check. So maybe write all these things. I will try to find this thing in previous lectures. So it is section number 3 with this Venus solution. So. Somewhere here. But in this case, instead of A, we use the channel matrix H. So you can see that let's compare. Like this one. So W Hermitian is equal, but here we use RSS instead of RXX. Then instead of H we use A Hermitian. Here A RSS, A emission plus the noise. And this thing can be written as follows. So using in multiplication with A's with noise parts, and here we'll have the inverse of the signal part. So let's rewrite this equation in the following way. So we will have, let me just check for 5 seconds. So A emission. So yes, let's go. Here we will have A emission times RNN inverse times A plus inverse of RSS, all this thing with inverse sign, times A emission times RNN inverse. And in this case, we can write down it is biased estimator. So we have biased estimator with blue color as before here, because if we multiply our weight matrix with array theory matrix, we will have something different from identity matrix of size D. And that's thing because here we have RSS. So let's see with, I will write just with pencil. If we rewrite all these things, we will have A emission RNN inverse times A, so this A, and in the denominator, so this one is numerator, so this part times A, we'll have A emission times RNN minus 1 times A plus the inverse of RSS. So of course we can say that if this part is equal to 0, we will have unbiased estimator. But we write down that we assume that this RSS is non-singular, and of course in this case all these multiplications are not equal to identity matrix of size D. So that's all for this part, and now we can go. Let's write for MMSE solution slides 16 up to 18. So here, slides 16, 18. And then here we have the last slide. where we represent this double information times A of mu, or in the same way we can write here, instead of special frequency, direction of arrival, so theta, and here for x-axis we'll have, instead of special frequencies, direction of arrival theta. And you can see that we will have something like this one. So for some special frequency here, we have the peak value equal to 0 decibel, and here we will have side lobes with less amplitudes in this case. So this one for antenna pattern here. Now let's go to the next. Not like this one, but like this one here. Yeah, unfortunately, I have no enough time for slides, so I will use grid slides. So let's write down multidimensional extensions. So T is 4.8. Multi-dimensional extensions. Multi-dimensional extensions. So before we had an 1D algorithms, so only for one dimension. So for example, this direction of arrival of theta, which can be represented, for example, as the angle along for x-axis, or we can say for x and y axis. And here we will start with 2 decays. So we have angle theta and angle phi. Which are called as co-elevation and azimuth respectively. And first, let's start with the slides from 1 up to 8. Slides 1 to 8. Yes, and set number 4. And let's start with how we represent our main task in these 2 decays. So here you can see 2D antenna arrays. We use azimuth for the angles between x and y axis. So we assume, so we denote it as phi subscript I, which is less than minus pi, and greater than minus pi, and less or equal to pi, or let's yes, pi. And another angle, we will call it as co-elevation angle with theta subscript I, which is between 0 and pi over 2. And it is the angle between this xy plane and z axis. So here we will start with extension for music first, and then we will go to 2D case for Aasp type algorithms. And here we can say that when we go to these multi-dimensional tasks, it is non-trivial task, and we need to have this combination with correct parameter pairs, which means the pairs between this elevation and azimuth angles. So next, we have this 2D music algorithm, which is expensive spectral search, then ad hoc schemes, and these Aasp type algorithms for multiple invariant space. We start with 2D music, and here we save the number of sensors to equal to m. As before, music algorithm can be, this one is applicable in case of arbitrarily 2D array geometry, so it is not centrosymmetric, for example. Then we need to add here another angle phi. Before we have only theta angle, and instead of 1D manifold, which is we are assumed as the rope, I think, before in 1D case, here we will have this manifold as the sheet in complex plane of size m. So we have the same measurement vector, but of course for A we need to add this phi 1, theta 1 up to phi g, theta g. We use the same steps. We calculate the singular well decomposition of x, in this case the matrix x as before. Or so first we collect these measurement vectors into the measurement matrix, then calculate SVD or EVD to estimate the noise subspace, and using this noise subspace estimation, we will search for these D maxima of this function. And let's show what we have in this case. So maybe one more time, if we look to the previous lectures. So, higher resolution parameter estimation, music algorithm. So this one and this one. So first, so yes, here you can see for 1D manifold, array manifold, we have a rope, so something like this one. And for this function of S, we have only theta value, and you can see we have nice picture with three sources. In this case, we say that we assume that we have three sources because we have three maximal points. And now let's show this function, but for values phi and theta, and we will assume that the number of sources is equal to 2. So for simplicity, here instead of x and y, we need to use three-dimensional picture, which is for z-axis. It is the values of this function s. So s music for phi and theta. Then for x, we will use theta, and for phi, we use y-axis. So y-axis for phi. And let's say that for source A, we have some values theta 1 and phi 1. And for second source, we have theta 2 and phi 2. So first, let's try to project where we will have these values on our plane. So like this one. Like this one. So in these points, we will have the maximum values. Something like this one, for example, here. Let's say like this one. And then we need to show that it goes like this one, like this one, for example, this one, and here I try to connect. Let's try to connect these two values, like this one, like this one, this one. And of course, the estimate of the G is equal to 2. And of course, this 3D picture can be represented using 2D pictures. So we can, let's say, project all these values to this plane as music for theta and as music for phi. So we need to project all these values on this plane. And we can, in this case, draw this picture, but with two values, or let's say like this one, because we have theta 1 and theta. Sorry, that's for music algorithm. Maybe we can add here, let's say, 2D spectral music. 2D spectral music. And then let's go next. Slides from 9 up to 20. So here we will go to 2D unitary Aasp algorithm. And this algorithm provides automatically paired azimuth and co-elevation angles. So we will see how we can do this thing next. So we can solve all these things in closed form, which means no searching required. It is computational very efficient. And yes, here we can find, for example, let's say two sources have the same theta 1, but they have different phi 1 phi values. For example, so it is next. I will write here just with pencil, but we will see it. For example, S1 has theta 1 and phi 1, and S2 has the same theta 1 but phi 2. And we can distinguish these two values using Aasp algorithm. So unitary Aasp. And the main idea, as before, for Aasp type algorithms, we can use different array geometries, but the main idea, they should be centrosymmetric. So we will see it next. Main requirement, centrosymmetric array with this exhibition that invariances in two distinct directions. Then this centrosymmetric means that our arrays are symmetric with respect to x and y axis. And the last point here, this let's say 2D unitary Aasp algorithm is amenable to an efficient DFT beam space implementation. So we will look to this DFT beam space just with one eye, let's say, but In guest lecture with Adele, we will go inside of this DFT beam space because he had this DFT beam space topic in his master thesis. So I will give you just some part of the information, and he will give you more detailed information with some implementations where we can use DFT beam space. So, but let's go step by step. First, okay, let's continue with the slides, and then we will continue with our notebooks. So we have the same 2D antenna. Antenna geometry. All these antenna geometries are center symmetric, and so here we assume XY plane. So X is here, Y is here, with delta X between belong X-axis and delta Y belong Y-axis. And here we will have different number of antennas for X-axis and Y-axis. So we will see it in the next slides. Here it is hard to see, but I think we will go next, and then if you want, we will go back to this slide in the future. So I think, okay, so let's write the slides, and then we'll have this grid picture how we choose array elements for 2 decays. So here we have slides from 9 up to 20. And overall direction of arrival can be represented in the following way. So we introduce z sub I, which is equal to u sub I plus j times v sub I, which is equal to the sine of the co-elevation angle times e to the power of j multiplied with phi sub I. Let's put this equation into a box. And we need correct pairing of these two values here. So this one and this one, correct pairing required. Correct pairing required. And I will show you what we have for u sub I and v sub I next. But first, let's show that co-elevation angle with theta I is equal to the arcsine of the absolute value of our new direction of arrival. So this thing is co-elevation. And phi sub I is equal to the argument of z sub I. And this one is azimuth. And now let's go back to the slide 20 and let's see what we have for u sub I and v sub I. So here you can see that u sub I is something like the projection onto the y-axis. This one. Sorry. No. For x-axis, because we show like this one. And v sub I is the projection to the y-axis. This one. And if we use mathematical things, here you can see that it is cosine of phi times sine of theta I, and sine of phi I times sine of theta I. And in the same way, we can rewrite this E, for example, as let's see, it is cosine first. Yes, so it is cosine of phi plus sine of phi. So multiplication of sine theta I cosine phi. It is our u sub I plus j sine theta I times sine phi I. This one is our vi, v sub I. So it is projection onto the x-axis, and this one is projection to the y-axis. If I'm not mistaken. So let me check. Sine times sine, it is v. Sine times cosine, it is u. Yes. And now we go next to slides 21 up to 25 here. 1. And we have this interesting antenna array. So you can see that for x-axis and y-axis, we have 4 elements. So overall, we'll have 4 times 4, 16 elements. And we choose these things using maximum overlapping. So, for example, you can assume, let's look only to this part with only these 3 elements for x-axis. In maximum overlapping, we will choose first, second, and third for the first selection matrix, and second, third, and fourth for the second selection matrix. But now we extend it, and we will choose, of course, first, second, and third, but for all these sensors, for y-axis also, and second, third, and fourth for this one. And in the following way, if we assume only the first row, let's say, so only these values for y-axis, we will choose, as before, first, second, and third, and second, third, and fourth for the selection matrix 1 and selection matrix 2, respectively. In this case, we will have 2 different shift invariance equations. So here you can see how we represent the selection matrices. And here it is the exchange matrix, but of size m sub x, where m sub x is the number of elements. So let's calculate all these things in our notebooks, and then we will continue with these slides. So let me switch here first, then let's switch here. So here we have slides 21 up to 25. We have uniform, in this case, rectangular array, URA. With number of elements equal to m. And we can find this overall number of elements as m1 times m2, where m1 is the number of elements for x-axis, and m2 the number of elements for y-axis. In this case, it is 4 times 4. And now we need to see what we have for so the number of elements in subarrays. We start with the subarray for x-axis. So the number of elements in subarrays of x is equal. So before, we write it as m minus 1. So it is the maximum overlapping. But in this case, we overlap over the x-axis. So instead of m minus 1, we write m1 minus 1. And we also choose all these, let's say, rows. If we look to our slides, rows of the array elements, which is in y-axis. So we need to multiply this thing with m2. And in the following way, we can show the number of elements for y-axis. In this case, we just write m1 and multiply this thing with m2 minus 1. So it is maximum overlapping over this y-axis. Let's put these two equations for the subarray elements into the box. And you can understand that in this case, instead of 2 subarrays, we will have 4 subarrays, because first subarray for x-axis and the second subarray is for y-axis. And here we can write down that m sub x is equal to 12, and in the same way m sub y is equal to 12. So let's look to our slides. So this maximum overlapping 3 times 4 and 3 times 4 with this dashed line, purple color. So maybe let's use this one. So this one, and this one. And in the following way, for y-axis, we have this selection matrix 4 times 3, and this selection matrix 4 times 3. So this one and this one. And let's see what we will have next. And here the main idea to see that right exchange matrix is the same, that of size m, and left exchange matrix, instead of just small m, we write m sub x and m sub y. And we will have these shift invariance properties for the steering matrix A. So this one for unitary esprit, sorry, for standard esprit. But then we can go to unitary esprit. So first we collect number of snapshots n, which is which should be equal or greater than number of sources into, and we collect it into this matrix. And then we need to find left singular vectors of transformed x. So we can continue. Or maybe let's make our break right now, and we will continue after 10 minutes. So then we will go deeply inside of this 2D Unity Aasp algorithm. Надеюсь, здесь понятно вот с сабарреями. Здесь достаточно трудно увидеть. Возможно, я вам так вскользь покажу, что мы имеем здесь. То есть жалко, что я вот не могу и там сразу вместе показывать. А вам здесь видно мышку? Ну так, слабо, да? Но для X у нас будет вот эти 9 элементов и нижние 9 элементов. А для, получается, Y у нас будет первые 8, то есть слева направо вот первые, так скажем, 2 столбца и вторые 2 столбца. А вот здесь надо уже чуть получше подумать, как они выбирают. Потому что, как я понимаю, это не просто вот так. То есть это не вот так и вот так. У нас потому что в таком случае оверлэппинга не будет между этими элементами. Они выбирают... Как они, интересно, выбирают-то? Но здесь еще можно понять. Это, скорее всего, вот так и вот так. Хотя... 1, 2, 3, 4, 5, 6, 7. Вот тут оверлэппинг только в 2 элементах будет. Это мало. Вот тут, например, 3 на 5 у нас должно быть, да? 3 элемента по X. Ну вот здесь, ладно, здесь еще более понятно. То есть по X мы будем брать, скорее всего, как я понимаю, вот эти 3 и вот эти 3. То есть только по вертикали. То есть 1, 2, 3 и 2, 3, 4. А по горизонтали для Y мы будем выбирать 1, 2, 3, 4, 5 и 2, 3, 4, 5, 6. Как раз у нас 6 элементов бывает. А вот здесь уже надо будет тоже прикинуть мозгами. Как-то нам интересно все это собрать. 4, 5, 6, 7, 8, 9, 10. Нет, я пока не могу вот сходу вам сказать, как интересно выбрать. Возможно. Ладно, я посмотрю. Ладно, давайте вот с этого момента 10 минут и продолжим в 25. Так, пока здесь останавливаемся. Здесь у нас запись идет, все отлично. Я, скорее всего, понял, как мы там будем выбирать. Для второго случая, для последнего надо подумать. Хотя... Я пока посмотрю. Интересно, здесь у нас есть нарисовать цветом. Угу. 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 Так. И здесь выбираем.
ошибки. Вместо того, чтобы вычислили принципы, какие функции надо записать в пейт, где мы так не забыла, что рекламировать нельзя, а пришло ведь формирование цвета России, а они там группа ничем не призывают, выявили некоторые культуры, естественно, ему, наверное, да и что-то там не пришла говорить. Так, если помочь. Собственно, что? Международной российской части разделяется. Да. Помню, писал, что больше абсолютно еще не бесплатники, а пилоты. Если ты делаешь, то все перевозки нужно выучить, ты можешь проверить, уже самый такси.
So let's continue our lectures. Here I show, I think, how we choose our selection matrices. So on this slide, you can see how we divide it for x-axis. So you can see here, for example, we choose first 9 elements and then second 9 elements. In this case, we choose this left part and right part. So first is top part and then bottom part. Here we choose only this vertical line of arrays, and here, as I understand, we will have only 2 overlapping sensors in this case. So here, for example, we have 6 overlapping. Here we have 4 overlapping. Here we have 2 overlapping elements. And here also only 2 overlapping elements. And what we have for y-axis. In this case, we choose 2 columns here and 2 columns here. In this case, we choose, let's say, this row and this row. And first, we choose first, second, and third elements, and then second, third, and fourth. In this case, we look only to this vertical line of elements, and we choose from 1 up to 5 and from 2 up to 6. And here we have the same case as for x-axis with 2 overlapping elements. Here we have 4 overlapping elements, here 4 overlapping elements, and here also 4 overlapping elements. So, great. Now we can continue with our algorithm. With these matrices for selection matrices, so J вы 421.
Да, ну, сегодня я постараюсь пораньше закончить.
Хорошо?
Поэтому
Хорошо.
следите за рекламой.
Хорошо.
Это опять, да?
Нет, все хорошо.
Вот смотри.
Но это еще с прошлого осталось.
Ну, я надеюсь, не с прошлого года.
Нет. So here we have J mu1 and J mu2 for let's see for x-axis. So this one, J mu1 and J mu2. So this one, and this one. And for J mu1 and J mu2 for y-axis. So this one, and this one, and here this one and this one. Great. And for the 2D case, we have two different special frequencies. First one, it is frequency mu, and second frequency mu. So mu for y-axis, x-axis. You can see here with delta sub x and projection onto the x-axis, it is u sub I. And for mu I, it is for y-axis. So you can see here delta sub I and the projection onto the y-axis, v sub I. Now we collect these n snapshots, and here we write down, I don't know, but n should be greater or equal of d over 2. So we need to collect more than 2 times of our sensors, something like this one. So, and here, let me check. Yep. So let's add here that n should be greater or equal to d over 2. Or, no, vice versa. So for example, if we have 4 sources, the number of snapshots should be greater or equal to 2. Then we start with signal source space E sub S, and here we will use first capital S as the true signal source space, and then we will go to the small s, which is the estimate of this signal source space. So E sub S, this one is capital S, is equal to the sparse left parallel matrix of size M with Hermitian times the signal subspace of matrix X. So U sub S with capital S. So it is the signal subspace of original measurement matrix, and this one is the signal subspace of the transformed measurement matrix. Then, as before, we can write down transformed array steering matrix D. It is the multiplication of the same sparse unitary matrix of size M with Hermitian, and here we multiply it with original array steering matrix. And as before, we can say that transformed array series matrix is somehow connected with signal subspace of transformed matrix X, where T shows the connection between these two matrices. Let's put this thing into the box. So one more time, here we use capital S. And this thing with red color. Let's continue with slides. Slides 26 up to 27. Okay, you can see first the review of 1D unitary Aasp. So it is our real valued invariance equations. The main idea here to see these transform selection matrices K1 and K2, which is the real part of this multiplication with selection matrix 2, and the imaginary part of the same multiplication. And we have this connection between transformed selection matrices. And we have this matrix omega with values on its main diagonal as tangents of mu sub I over 2, where mu sub I is our special frequencies. And now, let's go next. So here you can see the selection matrices for our 2D unitary Aasp. You can see that we use only the second selection matrices as before, here and here. And in this case, for transformed selection matrix for x-axis, we use only the second selection matrix for x-axis. So as before, the real part and imaginary part. And in the same way for y-axis, but with selection matrix 2 for y-axis. Then let's write what we will have for shift invariance equation in this case. So first here. We will have selection matrix K subscript mu subscript 1 times transformed Then array steering matrix times the matrix which contains our special frequencies mu. And it is equal to the second selection matrix. So K sub mu sub 2 times matrix D. Where matrix omega sub mu is the diagonal matrix with values tangents of mu sub I over 2, where I goes from 1 up to D. Let's use the same red color for matrix D here in the right side and in the left side. And let's put this equation into a box. And then let's continue here with selection matrices mu1 and mu2. So for y-axis. So it is K mu1 times D times omega with special frequencies mu, and here we have second selection matrix K sub mu sub 2 times D, and inside of this matrix omega sub mu we have values on its main diagonal equal to tangents of nu sub I over 2, where I goes from 1 up to number of sources small d. Red color for matrix D, and I will put this equation into the box. Then let's put, instead of D, this E subcapital S times T. Here and here, here and here. We will have selection matrix K sub mu sub 1 times E subcapital S times transform matrix T times matrix omega sub mu. It is equal to k sub mu sub 2 times E subcapital S and times T. And then, if you remember, we multiply both sides with inverse of T from right side, and we will have K sub mu sub 1 times E subcapital S times T times omega sub mu times inverse of matrix T, and it is equal to K sub mu sub 2 times E sub S. Of course, capital S. And to keep the same style, we can show with red color. This one is our D, so we just rewrite it using signal subspace and transform matrix T. And here, this one, and this one. So what is next? Let me check. Then we can say that this multiplication of T times omega sub mu yes, times inverse of T is epsilon sub mu, which is real of size D times D. And let's put all of these things into a box. And of course, we need to show in the following way all things for y-axis. So it is the same steps, but as the resulting thing, we will have matrix epsilon sub mu for special frequencies nu. So let's rewrite all these things for y-axis. K sub mu sub 1 times E sub S capital times T times omega nu. It is equal to K sub mu sub 2 times E sub S capital times matrix T. Then multiply both sides with inverse of T. So K sub mu sub 1 is sub capital S, then T matrix omega nu equal to the selection matrix K sub nu sub 2 times E subcapital S. And the red color for E subcapital S times T here and here. And then here. Then inverse of T and E sub S. And this multiplication of T, omega nu, and T inverse is matrix epsilon sub nu, which is real of size D times D. And the main question here is the following. So, if you remember, for the 1D unitary aspect, let me check. We have this matrix epsilon, which is eigenvalue preserving similarity transformation. And if we calculate the eigenvalue decomposition of matrix epsilon, we will find matrix, or as the eigenvalues, we will find the tangent of mu sub I over 2, and using arctangents, we can find our special frequencies. But in this case, we have two matrices epsilon, and we somehow need to find this automatical pairing of these values. And let's see what we have first on slides 28 up to 31. But maybe let's start with this one. So first we say when we rewrite the equation to the approximately equal. So equal to the approximately equal. This one for this equation and for this equation. And in the same way, this equation and this equation. Because we use least square solutions or total least square solution or structured least square solution. So LS, TLS, and SLS. And of course, we go from matrix E subcapital S, so true signal subspace, to the estimation of this signal subspace with small s. So here we have capital S, here small s. And next, slides 28 up to 31. 28, 31. I think on these slides we will see all this equation and then on other slides we will see how we can automatically pair the special frequencies. Oh. Sorry. So here we have this real-valued invariance equations for 2D unitary aspect. Then we have this real-valued eigenvalue decomposition for matrices epsilon sub mu and epsilon sub mu. And we need to find the correct pairing between these values of matrix omega. And let's write next what we have in this case. So we have matrices epsilon sub mu and sub mu, which is real valued matrices. So here we have epsilon sub mu and epsilon sub mu. They are real valued. D times D matrices. And we need a pairing between mu sub I, or we can use u sub I. So it is projection onto x-axis, and mu sub I, or the projection onto y-axis, it is v sub I. And then let's write down that automatic pairing is based on the following observations. Is based on the following observations. And here the pairing. automatic pairing with blue underline. So first, we have these real valued matrices. In this case, eigenvalues are also real values. But of course, sometimes we can get these complex conjugate eigenvalues. So first observation, eigenvalues are real valued. Eigenvalues are real valued. Then second observation, from the eigenvectors. So eigenvectors can be chosen to be real valued. Eigenvectors can be chosen to be real valued. As eigenvalues. And if we look to this shift invariance equation, you can see that we have the same transform matrices here. T inverse, and T inverse for the epsilon sub mu and epsilon sub mu. So these two matrices, it is our last observation. Matrix epsilon sub mu and epsilon sub nu have the same set of real valued eigenvectors T. Which is real of size d times d. Now let's put these three observations into the box, and then I will show you how we can use this automatic pairing. For this one, we have slides 32 up to 45. And the answer for correct pairing is this one. So we multiply epsilon sub nu with j and sum it up with epsilon sub mu. And then we'll have these, let's say, complex valued eigenvectors, eigenvalues. We calculate the eigenvalue decomposition of this thing, and the real part will be the tangents of mu sub I over 2, and the imaginary part will be the tangents of nu sub I over 2. And let's see next. So first we compute the signal subspace of, let's say, using SVD of transformed matrix X, or EVD of multiplication of this transformed X times transformed X function. Then we calculate these shift invariance equations using, for example, in easiest case, least square solutions. And then we sum up these two matrices, calculate eigenvalue decomposition, and we find special frequency mu as 2 times arctangent of the real part of eigenvalue, and the special frequency mu as the 2 times arctangent of imaginary part of our eigenvalue. So maybe let's write here. Let's see. Okay. So using, for example, we need to sum up mu epsilon sub mu plus j times epsilon sub mu, which is equal to matrix T times omega sub mu plus j times omega sub mu. This one can be denoted as matrix lambda, where matrix lambda is the diagonal matrix with values lambda I, where I goes from 1 up to z, and special frequencies mu sub I is equal to 2 arctangent of the real part of lambda I, and mu sub I is equal to 2 arctangent of the imaginary part of lambda I. So I think for today we can let me check what we have. Диак, то есть нет, мы можем в принципе сами значения взять, вот эти лямбды, ну то есть сейчас. Вот здесь лямбда Вот. Так. И здесь давайте запишем. So the number of sources. The number of sources. Let's switch here. Let's switch here. So here, dmax is equal to the minimum value between three values. So first value, it is the number of elements in subarrays with respect to x-axis. So m sub x. Then with respect to y-axis. And the last value here is the number of time snapshots, which is equal to 2 times m. It is because before we write that n is greater or equal to d over 2. So we just rewrite it with respect to d in this case. So 2 times n. And let's maybe indicate it with blue color here. To see that it is useful information for us. So I think we can go through unitary aspects. So what do you think? Are you okay to listen another unitary aspect but for DFT space? Or that's all for today? I can continue. Here we will have, I think, just one page because it is really interesting algorithm here. But if you want, we can continue. So it is just one page, but here I will give more information from my side. We will write only in few parts. So, okay, let's go to slide number 36 first. So here we need to see the comparison between element space. So it is the previous algorithms. So when we use unitary aspect, we can say that we search or not search, collect signals in element space. So what does it mean? So you can see that we, in this case, collect to our measurement vector all the values from all the array elements. But in the DFT beam space, you can see that we use first this discrete Fourier transform. And in this case, we will have less, let's say, in DFT beam space, it's called as sectors. sectors of interest. So we will have, for example, from all these M elements, only 5 sectors of interest in this case. And we will use these sectors for our direction of arrival estimation. Something like this one. So here, let's write another subsection unitary aspirate in DFT beam space. And this thing is important for massive MIMO and radars. And also we can use this focusing on the sectors of interest. So switch here, switch here. Unitary aspirate in DFT beam space. Unitary aspirate in DFT beam space. So you can see beam space. So we somehow create different beam formings. Let me check. Okay, so I think we can use blue color here to indicate this DFT beam space unitary aspirate. And for this one, we have slide number 36. Slide 36. And we start with 2 points here. Point number 1. This type of aspirate algorithm is important. For massive MIMO, which means we use hybrid analog to digital architecture. And also which is important for radars and radar. And then second point, point number 2 here, it enables focusing on a sector of interest with a reduced computational complexity. computational complexity. Because the number of beams is less than the number of antenna elements, or let's say array elements. So here we have the number of beams, which is denoted as capital B, is much less than capital M, where capital M is the number of antennas. So here, next, we show uniform rectangular array. Where the number of beams is equal. So B is equal to B1 times B2. And number of antennas is equal to the M1 times M2. So it is 2 decays. And here for some simulations, so maybe we will ask from Adele this part, because simulations, because I really do not know deeply with DFT beam space things here. So we have some simulations, and we, for example, use the number of sources equal to 3, the number of antennas or array elements is equal to 8 times 8, so it is overall 64, and the number of beams is equal to 3 by 3, so it is 9. And here we show this picture. So I have question for this picture. So we show it in the following way. So here we have y-axis for v sub I, and x-axis for u sub I. And here we show this point, which is equal to 2 centimeters, and here also 2 centimeters. and also one point here. And we will have something like, here we have the signal from source 1. Here we have the signal from source 2. And here we have the signal from source 3. But why like this one? It is really big question. Maybe we will see it on slides 37 to 38. So let's check. But the main idea here to reduce this computational complexity using the sectors of interest. So slides 37, 38. Yes, I think these. So it is our simulations where the number of beams is equal to 9, the number of elements is equal to 64, and the number of sources is equal to 3. Here we have also 64 snapshots, and we run all the simulations over 100 Monte Carlo runs, so or number of trials. And yes, here now you can see why we show it like this one. So the location of source 1 is U1, V1, which is equal to 0 and 0. Then U2, V2 for source 2 is 1 over 8 and 0. And for source 3, it is 0 and 1 over 8. So let's show here that this point here is equal to 1 over 8, and this one 1 over 8. So they are uncorrelated and they have the same power. And what we can see from these results. So we compare the results of our algorithms with respect to this stochastic Cramer-Rao lower bound, which is here, and which is here, this one. And what we can see here, they compare 2D unitary esprit in element space and DFT beam space. They use least squares algorithm for unitary esprit in element space, and also they use structured least square solution with one iteration. So first we calculate least square solution, then use this one as initialization for SLS and run one iteration. And let's see here. So for DFT beam space, we have bigger errors because we reduce, let's say, aperture in some case, because we collect the number of antenna elements only for one, let's say, в один поток, что ли, так скажем, one flow. And in this case, we have bigger errors, but it is really comparable. For example, let's say if we compare least squares for element space and least squares for DFT beam space with these experimental things. So you can see that here is difference between this circle and the cross. It is really small. I think it's something like 10 in the power of -4 maybe. But we reduce the computational complexity because we collect these all signals from array element from array into the less flows using DFT. But of course, if we compare it with SLS, it is approximately goes to this Cramer lower bound, but of course you can understand that when we use structured least squares solution, it is really complicated because we have all these structured things when we try to keep this relationship between selection matrices, and it is really complicated for 1D, but of course you can imagine what we need to do for 2D. So we somehow need to save all these relationships for two different special frequencies here. Then we have another simulations. What we change here? I think, yes, this one, this is root mean square error for source 2, and of course for source 1 and for source 3 respectively. Next, we go to harmonic retrieval problem for slides 39 up to 47. So let's write down this thing. We have on our slides (39) up to 47. And here we will have the 3 decays, I think. Then we use 3D antenna array. So first, let's start with 1D. So one-dimensional harmonic retrieval problem. Here you can see that we show here we have mu sub I. So it is special frequency for 1D. And if we assume 2 dimensional case, we need to show two special frequencies. So here we have mu sub I subscript 1 and mu sub I subscript 2. And then if we extend it to three-dimensional harmonic retrieval problem, we need to show all these three values. And of course, if we imagine 3D or RD, so where R is greater than 3, so it is 4, 5, and etc., we need to represent our sources as S multiplied with these all e to the power of mu sub I over R, and sum it up with the noise. So here, this one, for example, when we use matrix of size 2 times 2 times 10, I think. Let me check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. So in this case, it is better to use tensor representation of these signals, but of course we can start with matrix representation. So here you can see, first we write X for all zeros, so I think it is here, so all zeros, then 1, so M1, okay, let's go here as M1, here as M2, and okay, this one I think for R dimensional, but here we have only 2. Let me check. So this one, I think something like 0, 0, 0. Then if we go to the X1, 0, 0, and we need to, no, 0, 0, 0, then so with matrix representation, it is hard to see all these things. So it is easier to write, for example, value 1, 1, then, okay, let's start with this one, 1, 1, 1, 2, 1, 1, then 1, 2, 1, and 2, 2, 1, and then switch over this third dimension. But here, okay, maybe let's leave this one as follows, but here, yes, we can represent it using matrices, but in chapter 5 we will use tensor representation of all these matrix things, so it is easier to collect into the tensor. Yes, for example, here we have M1 equal to 4 and M2 equal to 3. So maybe we can start with this image here. M1, M2, let me check. Okay. So we have M1, M2, and we collect 5. 1, 2, 3. I just have, let me check, 3 and 4. Okay. So I hope I switch here. So we can represent all these things as follows. So for M1, we have 3 elements. For M2, we have 4 elements. Okay. And we assume also, so it is in our example here, M3 equal to 2. And this one for 3-dimensional case, R is equal to 3. And here we estimate a 2-dimensional direction of arrivals. So 2D angle. And also we estimate propagation delay estimation. Or we estimate propagation delay. Propagation delay estimation. Which is represented as follows. So mu, for example, sub I with this superscript 3 is equal to 2 times pi times our propagation delay tau sub I and times delta F0. So for this thing, we need to use an antenna array in the following way. So first, I will show you the first slice. So it is slice 3 times 4. 3 elements here for x-axis and 4 elements here. So it is 4 columns and 3 rows. So it is our K1. Here we have our K2. And now we need to show our K3. For this one, I will use blue color. So we need to show that this link is placed here, for example. It is first element. Here the second element. And here third element. So it is a rectangle in 3D space. So let's show that this one goes to this element, and this element. So we can show the structure of this antenna array. Next, let's show the second column. We will have something like this one, and this one. So we need to collect these things. Then here, and here, which is our third column. And the last column somewhere here, and here. Where, let's show maybe here, like this one. K3. And for these 2D angles, we will have mu I. It is mu I superscript 1, and it is equal to 2 pi over wavelength times the spacing between elements belong x-axis times u sub I, and the previous special frequency mu I is denoted as mu I superscript 2, which is equal to 2 pi over wavelength delta sub y times v sub I. And maybe let's rewrite this propagation delay. So here, to keep all these equations together. So this one for 3D case, and let's see what we have for 2D case. So easier one. Here we say that it is 2D case. In this case, R is equal to 2. So the number of dimensions. M1 is equal to 4 and M2 equal to 3. So it is our uniform rectangular array, and we need to collect 5 snapshots. If we collect it as tensor, we will see something like this one. So for x-axis, which is for vertical line, here we'll have indices 1, 2, 3, and 4. For horizontal line, we'll have these M2 with indices 1, 2, and 3. And time snapshots is collected as follows, and you can see indices 1, 2, 3, 4, and 5. And what if we try to represent it using metrics? In this case, we will write first row, so this 1, 1, 1, 2, 1, 3 here. Then we write second row, 2, 1, 2, 2, 2, 3 here. Then 3, 1, 3, 2, 3, 3, and the last one 4, 1, 4, 2, 4, 3. Then we go to the next snapshot and do the same things, but for snapshot 2, then 3, 4, and 5. And we'll have this, let's say, unfolding, but we will do unfolding in our ways. So it is something like unfolding. And as the last point here, we have an example of 3D harmonic retrieval problem with this r equal to 3. But I think we will go to this one in the next lecture. So yes, we need maybe let's see, 1, 2, 3, 4, and 5. I think we need approximately 5 lectures, and we will end with this theoretical part, and then I think we will start with practical things, but from section 3. So first we end with all this. That's later. With all these theoretical parts, what we need to do, how we can, for example, use adaptive filters in time domain and then in spatial domain. And then we will do the same things, but with practical implementations. And of course, I need to give you some information on tensor-based signal processing, which type of tensor decompositions we have, and in which cases we can use it. So that's all for today. So. Yes, we end our recording things here. So bye-bye. So thank you for today's lecture, guys.